Hello, my name is Matthew, and I'll be introducing our project using image processing and machine learning in order to detect COVID-19. So, a bit of background about our project. COVID-19 is a new disease that can be mild or extremely harmful to the human body, and symptoms are like that of the common cold. Testing for COVID-19 has allowed for early intervention, which has subsequently slowed rates of spread and rates of mortality. However, the tests that are being conducted have an approximate 2-day turnaround for individuals to receive the results. To help solve this, one can look at a CT scan of a patient's lung to detect signs of COVID-19 within the individual's respiratory system. With the help of machine learning and image classification, we could potentially lower the number of healthcare professionals and resources needed to manually check each CT scan. And this is done by training a classifier through various machine learning techniques paired with various feature extraction techniques. The COVID-19 CT lung image was collected from open source GitHub with total 746 images with 349 positive and 397 negative lung CT scans. The dataset has been confirmed by a senior radiologist in Tongyi Hospital, Wuhan, China. An example of a COVID positive and a COVID negative lung is illustrated on the slide. As a non-medical health professional, it is difficult to distinguish the differences between the two images. In the data pre-processing stage, we made sure that all the RGB images were converted to grayscale, since an RGB image will cause an error when run by a code. Also, we have resized all the CT scan images to a 256 by 256, as it is required by CNN and HOG to have the same input image size. And for the dataset, we have randomized, sorted, and separated the dataset in a 80-20 split between the training and testing dataset in order to evaluate the performance of the classifier. To choose the most suited hyperparameter for our classifiers, we have created a validation set which is separated from the test set in a 80-20 split.
Hello everyone, I'm HokHim Lai. In the following slides, I'm going to go through all the feature extraction methods that we use in the project. The first one is called histogram of gradients. It is also known as HOG. It is one of the most common feature extraction techniques used in the image processing industry. The idea is by extracting the image fixtures to improve the accuracy in the image classifications. By using HOG, it can help to remove noise and irrelevant data from the image. So the process that HOG using is to divide the image into smaller regions. For example, is 4 times 4 cells. So on the upper right hand side, that's one of the example of our CT lung image divided into a smaller regions. And after divided into smaller regions, it will sampling the slope of the shape and then allocating the gradient into our respect bins. So on the lower right hand side, that's one of the image show that how the shape is allocated to the representative bins. In this slide, I'm going to talk about the second feature extraction method that we use. It is called SURF. The full name of SURF is called Speed Up Robust Features. It is another very common feature extraction method used in object recognition and image classification area. The original idea of design SURF is It's a faster version of scale invariant feature transform. So SURF use Hessian matrix algorithm to detect the interest point, and then after that it detects the strongest descriptor from the surrounding pixels. So on the right upper hand side, there's one of the examples show that after we apply the SURF onto one of our city lung image, the data extracted from SURF is called SURF point, and it is a 2D dimensional data, and it cannot put it in a classification model to train them. So in order to train the cluster the models, another step is required. What we do is we try to cluster the extracted features, which is SURF point, to our visual of works, and then into a histogram. And after put those into a histogram, now we are able to put into the model and train the algorithm.
Support vector machines can be used in both classification and regression problems, where in this case, we'll be using it for binary classification. It is a method of supervised machine learning, which means that it uses training set to learn various features of the dataset and uses trained algorithm to test new datasets that do not have labels. They work by finding a hyperplane in n dimensionality in a given dataset into two classes. The hyperplane is chosen in a way that introduces the biggest possible margin between the hyperplane and any point in the dataset, which increases the chance of a new data point being classified correctly. Due to the nature of the data, there might be cases where data just cannot be separated cleanly. In this situation, a mathematical formula is used to translate the data into higher and higher dimensionalities until we can best separate the data with a hyperplane. This is known as kerneling. Due to its nature, SVMs are known to be accurate and work well with small and clean datasets. However, SVM is not without its cons. Due to the mathematical nature of translating data into higher and higher dimensionalities, it doesn't look well with larger datasets, as the training time can take too long. If the data is noisy, then there can be too many cases of overlap, thus reducing efficiency. This is the demonstration of SVM SURF for COVID-19 detection in CT lung scan images. First, we load training and testing images using the command image data store into a variable. We take from the folder train resized or test resized, and the pre-processing steps are already done from Parallel code. And we attach labels to it using SQLS read from the file train label and test label.xlsx, and then we sort these labels. Next, we feature extraction using surf and surf. We visualize the surf. First, it takes a while for the program to extract all the surf features and regroup into a bag of values. We just use the bag of features command from MATLAB with the train set from variable we established earlier, and then we just read the image and extract the training features using encode. Next, we can view a histogram of the features, just using a figure and bar. And with this, we can see the visual word index and frequency of occurrence using this graph. We can see that one is particularly spiky and the rest are kind of random. Moving on, we can train our SVM using train image category classifier, which is built into MATLAB, using our train set and the bag of features we just got in here. So after we train our SVM, now we can extract surf features from our test set for comparison later. Next, we evaluate our classifier with the train set just for a sanity check. Now, this should be relatively high, but we get quite a low accuracy, and this will come into play later. But next, we should evaluate our classifier with the test set. Now you can see here that the average accuracy is quite low with many false positives and many false negatives, but this is fine because we want a high false positive rate, but we want this to be lower, and that will be possible through hyperparameter tweaking. But later in our other methods, we will utilize a neural network in order to extract the best hyperparameters.
One of the image classification techniques we used to process COVID-19 CT scan images was the KNN classifier. KNN is short for K nearest neighbor, and it is a basic learner which is easily understood and implemented. The classifier works by locating a point of interest and calculating the K amount of nearest points based on Euclidean distance. In the next slide, we'll see a demonstration of our KNN classifier being used. Hello, today we'll be doing a demonstration of the HokKNN classification of our COVID CT scan images. Okay, so starting off, we import our resized pre-processed COVID database. Clear any labels that might be there. Input our labels, so our training labels and our testing labels. Next, we read over an image and apply the hog feature extraction to one image just to test, make sure the right thing is going to happen when we loop it over all of them. Using cell size 32, found this to be the best. With the lower numbers, yes, we had more features, but the KNN classifier seemed to be distracted, and just having so many features led to less accurate results in the end, so 32 seemed to be the best. After that, we were happy with our feature extraction of the image, so we looped over the whole training set, applying the same process. Then we built the classifier using the fit-C-KNN that MATLAB provides. This was included our training features and training labels. Then adjusted the number of neighbors, which is K, initially as 1, but we found 10 to be the best, the most accurate. Next, imported the test images and extracted the features from them. After that, after it looped through all the test images, we then made a prediction with the predict through MATLAB and used the classifier results and the test features. After that, we evaluated the KNN classification of the images with a confusion matrix that compared. It was comparing the test labels compared to the predicted labels. So if we run this quickly, it doesn't take very long to compute at all. We can see in the command window of MATLAB. Here the classifier is shown, class name 0 and 1 indicating COVID and non-COVID. Number of observations in the test set, we had 596, which was about an 80% split of the whole database. The distance Euclidean, which is used in the KNN classification. The number of neighbors, as described before, 10, which was the best for us. And here's the confusion matrix results, which is how we evaluated our classifications with different feature extraction methods and tweaking different parameters such as the number of neighbors. So here we can see a high number of true positives, which is good.
In this session, we'll talk about the convolutional neural network used for training the COVID-19 detection CT image. A convolutional neural network, CNN, is a neural network that has one or more convolutional layers and are used mainly for image processing, classification, segmentation, and also for other autocorrelation data. A convolution is essentially sliding a filter over the input and looking at a function's surroundings to make better and accurate predictions of its outcomes. The most common use for the CNN is image classification, in our case, the COVID-19 image detection. As you can see in the slide, left side, we start from importing the dataset and separating the dataset into the train and test. And then we will separate the validation from the test dataset, and we will import the GoogleNet, which is a convolutional neural network pre-trained from Google. And then we'll create a layer for our own training model, and we'll create training options. After that, we'll create training nets with the dataset layer and options that we've created. Then we'll train the model, and then we will predict the test dataset with the trained model, and the accuracy will be shown. The right side shows you how we have implemented the Google Nets and how we created the layers and how we have them options. Now we'll see a video of explaining how GoogleNet works. Jugyeong Kim, and I'll be explaining you about how CNN GoogleNet works. First, we're going to be importing the COVID-19 database to the train image. Next, we're going to be inputting labels to all the images. And then we're going to be separating the train image and test image from the database. 80% will become the training, and then 20% will become the test image. Now we're going to separate the validation image from the test image. 80% will become the test image, and the 20% will become the validation. Next, we're going to import the GoogleNet, and then we're going to create the layer for GoogleNet training for the model. As you can see, the image is resized to 256, so we are going to input an image size of 266 multiplied by 256. The next one is we're going to erase the last layer in order to make sure we can put our own fully connected layer with value of 2. And we're going to have to finish with a softmax layer. Next, we're going to set up the options for the training. I've set the options as SGMD, initial learn rate of 0.05, max epoch is to 20, shuffle is only once, data validation data is train image validation, where we actually did here. We have separated the validation from the test image. We're going to use it here. And the frequency is 10. The variable says true. And next thing, we're going to be creating the training net out of the layers, options, and the database. So as you can see, net equals train network, train image, the images from the training, and the layers, which we have already created for the model, and the options that we have already set. Next thing is we're going to predict the test dataset by using the net trained network. So why predict classifiers net, which is the network, and the training image was the training image. We're going to try the validation equals training image validation dot labels. So we'll calculate the accuracy by summing the predictions if the predictions are correct with the validations, which are the test, which are being tested while on the training of the model, and then divided by the number of validations. And next, we will be actually testing our images to the test. As you can see, y predict is a classified net and test image. Now, y test is test image and labels. So the accuracy will be similar to this one. Sum of the y predict test predict equals to y test. You'll see how many are correct, and you'll divide it by how many are there. And then you'll display the prediction accuracy, and the accuracy will be displayed. Now we're going to run this program and see how it works. As you can see, it's working. And soon the training process will pop up. Yep. So as you can see, this shows you the training process of how the loss value decreases as each process and how the accuracy increases. You've seen a validation accuracy 100, which is not bad. Now here is the accuracy of the test prediction, where you're testing with the accuracy of the test databases. According to the evaluation, we have figured out the classification model accuracy for SVM and KNN. According to the chart, we can see that SVM and KNN both using HokHim and Surf. SVM with HokHim shown 51%, SVM with Surf shown 51%, KNN with HokHim shown 59%, KNN with Surf shown 56%. Both didn't show a good accuracy, however, we could assume that KNN is more adequate to the specific dataset predictions. But however, we could also assume that both KNN and SVM is not really adequate for such complex datasets as CT lung image. However, we can see on the bottom, CNN training with GoogleNet layer has shown an impressive accuracy rate of 93% and shown successful predictions to the image. Multiple layers of feature extractions might have been the key reason why CNN shows higher accuracy to this complex CT lung image dataset. That's the end of our presentation. Thank you for listening.